everyone, and welcome to today's lesson. Today we will be mainly doing the lecture in the video, and there's going to be a lot of things you'll have to do on your own. So the lecture will be in the video. Homework review, it won't really be a review, but this is a reminder to turn your homework in online. Okay, please turn it in online. If you have any questions about homework, please email me. Also, this table right here, Theorems and Postulates table, also may be called Definitions and Postulates table. This is on my SJ. All right, you will need to have this printed out. Okay, you may be able to use this in future on tests and quizzes. However, you cannot use it if you have an electronic copy. You can only use it if it is printed out. So go ahead and do that today or sometime this week, as soon as you can. That way you can start writing on it. And it is posted on my SJ. That being said, let's get started. Now, today we're going over conditional statements. The nice thing about this lesson is it should be a bit of review from last lesson. Now, if you remember last lesson, we talked about statements in general, and I mentioned that most have the pattern of an if-then pattern, okay? Here's where we get into that. Because if-then pattern has a name, and that name is conditional statements. Okay, conditional statements. Okay, again, here is the reminder that P and Q are the variables used. Okay, so most conditional statements are phrased as, most commonly, if P, then Q. But these are other common examples if you see them in your book or in a definition. So P implies Q, and then this arrow also means then. So this one is read as if P, then Q. So all three of those things mean the exact same thing. Now, if you forgot to write it down last time, here's a reminder that P refers to the hypothesis. All right, and Q refers to the conclusion. So I'll point out to you right here, please pay attention that Q and P, these two variables, are not attached to if and then. Okay, they come afterwards. And I'll get more into that in the next slide. But please make sure you note the difference that you have the words if and then you have P and Q. All right, let's go into why that's important. So, not all conditional statements will be written in if-then form. There's a lot of statements we make in our life that aren't in the if-then pattern. However, the logic still is there. So we need to be able to identify the hypothesis and the conclusion of any statement, and then be able to write it as a if-then statement. So in this example right here, we have a reptile is a cold-blooded animal. Okay? The hypothesis is going to be kind of your subject. Okay, it's the main thing you're talking about. And the main thing I'm talking about is the reptile. Your conclusion is, well, the conclusion. So what comes after or what comes next? And that is cold-blooded animal. Okay? So your hypothesis is going to be a reptile. That's the main thing we're talking about. And then your conclusion is going to be cold-blooded animal, since that is what is describing the cold-blooded or the reptile, or is what we're talking about. And that is not how you spell animal. There you go. And now that we've identified these two pieces, I can write it as an if-then statement. Now you can add the occasional word to make it flow as a sentence, but don't try to change any of the words, because then you could screw up your hypothesis or your conclusion. So I'm going to write, if it is a reptile, it's an L right there, then it is a cold-blooded animal. And that is how you would write it. Now, I changed the color of if and then because I want to again make the point I made on the last slide. If and then are not a part of the hypothesis and conclusion. Okay? The hypothesis is what comes after the if. The conclusion is what comes after the then. Okay? If and then are markers. They tell you where it is, but they are not a part of it. So on a test or a quiz, if I say label the hypothesis or label the conclusion, and you include the if or the then, you may get a half point off because those words only serve as markers, indications. Okay, they're not a part of the actual hypothesis and conclusion. So make sure you do some sort of color change like I did. That way it's clear in your mind which piece goes where. All right, now in a little bit I'm going to say pause the video now. And what I want you to do when I say that is to write these examples down in your notes and then try to rewrite them as if-then statements. When you're done and you've done your best, play the video and you'll see my responses. Okay, go ahead and pause the video. How'd you do? Hopefully well. As a last reminder, please resist the urge to add information. Okay? Only use the information that is given to you. You can add a small word like they or it, okay, just to make the grammar of the sentence make sense, but please don't add any new content. That being said, let's move on. Now, conditional statements are a compound logical statement. And what this means is the truth value of the statement relies on the truth value of the pieces. Okay? So a conditional statement is true if the conclusion is true. In every case, the hypothesis is true. So if the hypothesis is true, if that is a true statement, and the conclusion that follows is also a true statement, then the conditional statement itself is a true statement. However, if your conclusion is false, okay, if the conclusion is false in a case where the hypothesis is true, then the statement itself is false. This is what we were doing last class with the counterexamples. Okay, so think about the statement, if you are a teenager, then you have an iPhone. Now, every class had their own local hero, which there was a kid who did not have an iPhone, and so there was a counterexample in every single class. What this means in terms of this statement. In every class, our hypothesis was true. The piece of if you are a teenager was true in every single class. Okay, everyone who didn't have everyone in the class, besides me, but I wasn't counted, everyone in the class was a teenager. So the hypothesis was true. However, our conclusion was false because this says you have to have an iPhone, but there were cases in each class where someone didn't have an iPhone. Okay, therefore, this whole statement is false. Okay, so even though the hypothesis was true, every class, all of you guys were teenagers, the conclusion was false because in every class there was at least one example of someone who did not have an iPhone. Okay, now this is really important to picking out the true and false and keeping your eye on which one is which. Okay, but if you can keep it in your head like this, you'll be doing fine. This last bit of a conditional truth table, you can just ignore this piece. We're not doing that. If you got this written down in your notes and you have a sense of what I said, then you're good. If you want to replay that piece, this past slide, so you can write that down, that'd be an excellent idea. Now, I want to make a point that may not make sense at first, but I promise the logic is sound. On the last slide, you may have noticed that in each example, the hypothesis was true. Okay, you started out with a true hypothesis. So some of you may have asked yourself, what happens when the hypothesis is not true? Here you go. So when the hypothesis is true, you can draw a conclusion and you can determine the truth value. Okay, if the hypothesis is true and the conclusion is true, then it works. If the hypothesis is true and the conclusion isn't true, then it doesn't work. However, when the hypothesis is false, then the truth value cannot be determined. And if you can't determine whether it's true or false, the statement is just considered true by default. Okay? So if ever you have an instance where the hypothesis of the conclusion isn't true or just doesn't even make sense to begin with, then you can't go anywhere. There's nothing you can conclude or determine or anything. And so as odd as it sounds, what that means is that the statement is considered true by default. So an example of this would be, if pigs fly, then dinos rule the earth. Okay? Now, pigs don't fly. Alright, I know some of you probably have about 4 different sarcastic responses about pigs and airplanes, but pigs themselves do not have wings and therefore cannot fly under their own power. So, in this instance, the hypothesis and the conclusion, they don't even relate to each other. But it doesn't matter because the hypothesis itself is false. Okay, this is a situation that cannot happen. So, because the hypothesis is false, the whole statement is considered true by default. And that's just the way it is. Now, these bottom 2 examples, I do want you to have in your notes. So in a moment, I'm going to say pause the video. What you're going to do is you're going to write each of the examples, determine whether they're true or false, and then play and see if you got it right. Okay, then go ahead and pause the video. How'd you do? So the first example was true. If you have 2 vertical angles, then yes, they have to be congruent. That's part of the that's part of the postulate we talked about. However, the next one, if 2 angles are supplementary, then they form a linear pair. That is false, because I can have 2 supplementary angles that are not a linear pair. And as you can see, I even illustrated my counterexample over here. So if ever you're going to declare a statement false, remember, this is geometry, you have to defend. You need to make sure you either write or draw your counterexample. Okay? Now, some other related statements with conditionals are these 3. Converse, inverse, and contrapositive. What I want you to do is focus on the symbols over here. A conditional statement, as we've been talking about, is if P, then Q. A converse is when you flip them. It's now if Q, then P. Now the inverse is when you negate the conditional. So remember, this little symbol right here means not. So if not P, then not Q. And last but not least, our contrapositive is when you negate the converse. So we have not Q, then not P. Please make sure you have these in your notes. They're going to be very important as we move forward. Go ahead and pause the video and do the example down below. How'd you do? Make sure you check your answer with mine, and we will move on. Now, taking that statement from the last slide, I'm going to put it in this chart. So here is my conditional. If 2 angles are a pair of vertical angles, then they are conditioned. Remember that this is our hypothesis, P, and then this is our conclusion, Q. Underneath it, you see written out the converse, the inverse, and the contrapositive way of writing that conditional statement. Okay? Please make sure you have this table in your notes. It's going to be very important. Now, I've gone ahead and I've labeled the table in terms of P, Q, not P, not Q. So now that you have this written down, and hopefully you have it labeled, the question I want to ask is, what are the truth values of these statements? Okay? Ignore this truth table bit. I'm not talking about that. But look at the statements and see if you can pin down which ones are true and which ones are false. Go ahead and pause the video. And here we go. these are my answers. Now, as you can see on the converse, when I said they were false, I drew my counterexample. So there, the statement says if two angles are congruent, then they are vertical angles. And here I have an example of two angles, not vertical angles, but still are congruent, as you can tell by the congruency markings. Now, this last question, do you notice any similarities about our table right here? Notice that the original and the contrapositive, so the conditional and the contrapositive, are both true. And notice how the converse and the inverse are both false. This is a pattern that will always happen, okay? This will always be the lineup. The reason this is because they're related statements, okay? So when you have related statements, they are said to be logically equivalent, which means they will always carry the same truth value. So the conditional statement and the contrapositive will always be true or false together. The inverse and the converse will always be true or false together. Okay? These pairs will always be logically equivalent in every case. Converse and inverse. So if ever you're on a test or quiz and you get confused by the statement itself, you can always remember that these pairs are logically equivalent, and that will help you remember whether or not the statement is true or false. Okay? Now here's what I mentioned at the very, very beginning of the video. On my SJ, you're going to find a postulates and theorems table or a definitions and postulates table. I forget what it's called. Go ahead and print that out. And what I want you to do is in the definitions section of the table, you're going to write all of your postulates and theorems that we've learned so far. Okay, and I have a little selection as a reminder. These are the ones we've done so far. Okay, you're going to write them down, and then in the example box, you're going to draw your pictures. And make sure these pictures are detailed. Okay, like for segment addition postulate, we've drawn pictures before. Angle addition postulate, you've done homeworks with that before. Okay, for vertical angles, don't just draw me an X or draw yourself an X and move on. Okay, mark them as 1, 2, 3, 4. Okay, be detailed about your drawings, because remember, it's not the best. Because remember, you could be able to use this, or you will be able to use this on future tests and quizzes when allowed. Here are the instructions as well as a few others from what I said last slide. When you print out the table, I want you to rewrite each of the postulates that we've learned so far in the definitions table as if-then statements. Okay? So you're going to rewrite each of the postulates as if-then statements. You can find this in a table in one of the chapter 2 sections. I'm not for sure which one. You can find it though. Now, you're lucky because postulates 2.5 through 2.7 are already in if-then form, but definitely 2.1 and 2.4, you're going to need to rewrite them as if-then statements. Once you've written them, go ahead and draw your examples, and please make sure you use symbols. You really need to get used to seeing the symbols and being able to connect the symbols to the definition, so that when you see the definition or the statement, you can draw the picture, and when you see the picture, you can understand and remember the statement itself. One last thing before I let you go, we have one more statement to consider. This one is called a biconditional statement. Bi meaning two. So what this means is that it will be true going in both directions. Example to follow. Consider if two angles are complementary, then the sum will equal 90. Go ahead and write out the related statements, so the converse, inverse, and contrapositive, and try to determine their truth values. Pause the video. All right. Now, the way I did it was I labeled my conditional statement with P and Q, and then off to the side I wrote down my little math symbols. That way I could keep straight in my head which one was which. So this top one, the order it goes in is converse, inverse, and contrapositive. Okay? So 1, 2, 3, 1, 2, 3. Get used to the math symbols, though. That's going to be a really big help, and it'll help you on tests and quizzes because it tells you the order and where things go. Now, as you can see here, my statement's all written out, and you may have noticed by now, if you determined the truth value already, that the condition of the original statement was correct, and that every single one of the related statements was also true. Okay? So it wasn't like in the previous example where some were true and some were false. In this instance, all are true. These instances are what's called biconditional statements. And that is the instance where all, the conditional and the related statements, all of them are true. Now, when this happens, the way you write the biconditional statement is with the phrase, if and only if. You have to have the phrase, if and only if. Okay? And what this allows you to do is combine the conditional and the converse together in one sentence. Now, there is an abbreviation you can use. If you use IFF on a test or quiz, I will accept it. But if I ask you for a biconditional and you don't give me if and only if or IFF, then technically you didn't write the statement correctly. So please make sure you have this starred in your notes. And the way we write this mathematically with symbols is with this double-sided arrow. P, if and only if, Q. And the way this would look is shown down here. These are two different ways you can write them. Both are completely true and valid and will give you full credit on a test or quiz. The first one, two angles are complementary if and only if the sum of their measures is 90. True statement. Or the other one, the measure of two angles' sum is 90 if and only if they are complementary. Both are logically sound and both are written correctly with the IFF in the correct spot. Now, last thing I want you to know is on this slide, there is no if and there is no then before and after the hypothesis and the conclusion. Okay? So this only says two angles are complementary if and only if the sum of their measures is 90. There's nothing up front and there is no then here in the middle. We only use the expression if and only if. Okay, so please make sure that when you rewrite your biconditional statements that you write it correctly with the if and only if in the middle. Now, most of your biconditional statements will be definitions. Okay, so a lot of the definitions, we've done a few examples so far. Vertical angles, complementary angles, those can be written as biconditional statements because they're definitions. Okay, both parts have to be true. But so far, this whole PowerPoint, we've only done things in words. Last thing I want to talk about is doing the same thing, but in math, okay, in symbols. We're getting to the part in geometry where we're doing proofs, and you need to be able to understand your symbols. Otherwise, you're going to be lost, okay? So let's just use for an example the definition of congruency that we learned back in Chapter 1. Now remember, if two things are congruent, then their measures are equal. So if I have a line segment AB that is congruent to line segment DC, what that means is that if this is 50, then this is 50. Well, the way I would say this in math is right here. Okay? Segment AB is congruent to segment DC if and only if the measure of AB is equal to the measure of CD. Okay, this is the mathematical way to write this sentence. What I want you to do is try to write it in words using the if and only if. Pause the video and try it. And there it is. How'd you do? Please make sure you have the correct phrasing in your notes, and we'll move on. Now that we have an understanding of biconditional statements, I want you to look back at your definitions, postulates, theorems, whatever table. Okay? Now beforehand, I told you to write the postulates and theorems that we've gone over as conditional statements, as if-then statements. Well, it is also a definitions table. And as we just discovered, most definitions can be rewritten as biconditional statements. So you may already see where this is going. What I want you to do is write the definitions. Rewrite each of your definitions as biconditional statements. So by the end of this, you should have your theorems and your postulates written down as conditional if-then statements, and your definitions written down as biconditional statements. You do all this correctly, and like I said, you may be able to use this on tests and quizzes moving forward. This chart will be especially helpful as we add more postulates and more theorems. It's just nice to have them all in one singular spot. Alright, that is it. That's all I have for you guys. Thanks for bearing with the long video, and I'll see you next time.